Good morning everyone. This is a new content for you, that is applications of Cauchy's theorem. It has so many lessons included in it. Let's have a look over them. Alright. The first one is proof of Cauchy's first integral formula. Then are the exercises on Cauchy's integral formula, Taylor's theorem, expansion of Taylor's series, Morera's theorem, Cauchy's inequality, Leibniz theorem, fundamental theorem of algebra, maximum modulus theorem, and the last one is Schwarz's lemma. This lemma I had already done in my YouTube video channel. You can have a check over it. Alright, now some of the remarks. The first one is, if fz is analytic in a simply connected domain D, we know that integral over C fz dz is 0 along every closed contour C contained in D. So whenever you are having a function to be analytic in a simply connected domain D, then the integral over that function is 0. The second one is, when a function is analytic at all the points but a finite number of points, all but finite number of points, we have integral over C 1 over z minus z naught dz as 2 pi iota along every positively oriented simple closed contour C containing the point z naught. So now what are we waiting for? Let's start with the proof of our theorem, that is Cauchy's first integral formula. The theorem states that let fz be analytic in a simply connected domain containing the simple closed contour C. If z0 is inside C, then f of z0 is equal to 1 over 2 pi iota integral over C fz over z minus z0 dz. Now if you look at this figure, I have drawn a contour C, and inside that I have drawn a circle C1 centered at Z0 having the radius R. Whenever your function is analytic, obviously that function is continuous. So let's start with the proof. Now since f is continuous on its domain and particular at Z0, let's use the definition for continuity of the function. Therefore, for given epsilon positive, we can construct a circle that is C1 z minus z0 is equal to R inside C and small enough that so that this mod of f of z minus f of z naught, this is less than epsilon for all z on C1. Let's mark this as your star. We will be using this later on. Now, the next step is, now by Cauchy's theorem for multiply connected region, we are applying that theorem on this multiply connected region. We are having C and C1. Since the rotation is positively oriented on C and inside the rotation is opposite one, the orientation is opposite to C, So when I apply this theorem, Cauchy's theorem, on C union C1, the sign of C1 changes to negative because of the opposite direction to C. So now let's apply by Cauchy's theorem for multiply connected region. Integral over C union C1 f of z over z minus z naught dz. This is equal to 0. Okay, so next, integral over C f of z over z minus z naught plus integral over C1 f of z over z minus z naught dz. This is equal to 0. Now this sign will changes to negative because of the opposite orientation of C1 with respect to this C, which implies this integral over C f of z over z minus z naught dz. This is equal to, take this on the other side, you will be getting C integration of C1 fz over z minus z naught dz. The next step is, now I'm adding and subtracting f of z naught here. F of z naught plus f of z minus f of z naught over z minus z naught dz. Let's now separate this. Integral over C1 f of z naught over z minus z naught dz, and the other one is integral over C1 f of z minus f of z naught over z minus z naught dz. Fine. Alright. Now this is your constant. Let's take it outside. F of z naught integral over C1 1 over z minus z naught dz. Now this whole thing will be equal to 2 by iota. Just check your remark 1 plus integral over C1 f of z minus f of z naught over z minus z naught dz. So this thing is 2 by iota. Let's check our remarks. I have mentioned it. The second one, when a function is analytic at all but finite number of points, we have integral over c 1 over z minus z naught dz as 2 pi iota. I'm using this now. So just write over here, this is f of z naught 2 pi iota. Fine. Plus integral over c1 f of z minus f of z naught over z minus z naught dz. This is your integral f of z over z minus z naught dz. Now when this second term removes, or when it tends to 0, we will get our result. Yes. Let's check the mod of the second term. Since the mod of integral c1 f of z minus f of z naught over z minus z naught dz, this mod is less than equal to integral c1 mod of f of z minus f of z naught over z minus z naught mod and the mod of dz. Now this mod of fz minus f of z naught is less than epsilon by our definition for the continuity, which we have marked as star. This mod is less than epsilon. So just write this as, this is less than epsilon over this mod of z minus z naught is r, and then remained integral over C1 mod of dz. What is this? This is nothing but your circumference of the circle of radius r. So this is epsilon. This is 2 pi r over r. R cancelled. You will be left with 2 pi epsilon. Now 2 pi epsilon is your positive. This is positive. Epsilon is also taken as your positive. Now epsilon can be any small positive real number, that is, it can be 0.000234 so on. You can take any epsilon as required. So this mod is now strictly less than 2 pi epsilon. Without this mod, can I take this as f of z minus f of z naught over z minus z naught dz? This is equal to 0 because the mod of this thing is less than 2 pi epsilon and epsilon was arbitrary. So you can write over here, since epsilon was arbitrary, it is a very small positive number. You can take this as 0.00012 or 0.00034. So this 2 pi epsilon tends to 0. So if this mod is less than 2 pi epsilon and it is tending to 0, then without this mod, this thing is equal to 0. So just putting back this this thing to be equal to 0 over here, and you will be getting integral over c f of z minus z naught dz is equal to f of z naught 2 pi iota. Take this 2 pi in the denominator and you will be getting f of z naught is equal to 1 over 2 pi iota integral over c f of z over z minus z naught dz. This is your required Cauchy's first integral formula. Alright? Okay. Here the proof ends up. Next, there is a theorem for you. Let fz be analytic in a simply connected domain consisting the simple closed contour C. Then fz has derivative at each point z0 inside C with f dash z0. This is your first derivative of fz at z0. That is equal to 1 over 2 pi iota integral over c fz over z minus z0 whole square dz. Alright. So the next one is, now if you have the first derivative, the power is increased to plus 1. If you having the second derivative, then this power will be 3. If third derivative, then this power will be 4. Just increased plus 1 power. Okay. Now there is a remark. Let fz be analytic in a simply connected domain containing the simple closed contour C. Then fz has derivative of all orders at each point z0 inside C with. Now this f and z0, this is your, wait. Now this f and z0, this is your nth derivative at z0. This nth derivative of fz at z0 is equal to n factorial over 2 pi iota integral over c fz over z minus z0 n plus 1 dz. Alright. So if you are having the first derivative, then this will be 1 factorial, which can be as 1, and this is square. If you're having put n equal to 2, the second derivative, you will be here 2 factorial over 2 pi iota and fz over z minus z0 2 plus 1, that is 3. The power increased to 3 and so on. So this is your Cauchy's integral formula for nth derivative. So when we do the exercises, we apply the formula according to the derivative we need. So if you need the proof of these two results, then you can mention that at the comment box. Right now we are not discussing the proof of these two results. We just, in the next video, we will be doing the exercises based on this Cauchy's integral formula, and if you need the proof you can mention that in the comment box. And do subscribe my channel for latest videos. So thank you for watching.